I'll let them go for that one.
That is a good idea. Question?
Yeah, I'm having trouble using getAddr info.
Okay.
Are you using the HTTP address?
I'm passing it the string HTTP as the second parameter. And I'm passing it the host name parsed out like HTTP www.google.com.
The HTTP part doesn't work. You have to get the other host name when it comes down to the host colon. Like just www.google.com and HTTP:// from my experience.
And there's no difference between the two strings. You can't look up HTTP:// obviously, but as long as you extract the host name, either one's going to work because they're identical. They're just strings.
Well, not the HTTP difference.
Oh, that's not part of the host name. So you got to remove the HTTP:// if you want to use that one. Yeah. Yeah. Maybe, is that?
I'm
pretty sure that's not your problem. Let me see here if I have an example of getAddr info that we can pull up quickly.
I guess what do you recommend on passing in hints because it asks for hints?
Yeah, so you want to give it, you want a sock stream, and you want HTTP, I think. So doesn't that go in there? I haven't used this much, but I did just use it for this solution. So let me see if I can. I've always used get host by name, which is the old school way, which stinks compared to this one. So I'm just learning with you guys here. Let's see if I can find it. Okay, so here we are. I will just show you my part of that solution because we don't want to waste time on this. Nice. Okay, let's not go there. Let's see if this goes better. Ever so slightly. Okay, whatever. So what are we doing here? Maybe this is something you're tripping up on?
No, I'm doing that.
You are not knowing it? Okay, so I have AFINet, the sock stream, that's it. Then HTTP for the port there.
Okay, I might be parsing it correctly.
Yeah, so try printing out the host name and make sure that you have it right. It could be that you got a /r/n in the host name there. If you're grabbing it from the second line, from the host colon line, that might be it. Okay, so topic of today is, well, we're actually starting on concurrency, but we'll do concurrency in a network setting first. So what does concurrency mean? Well, it's the fork. All right, we've done a bunch of forking already, but we haven't really seen the troubles that concurrency gives us. And then there's also, so fork creates lots of processes. All the processes are independent of each other, right? They have their own address space, they have their own everything. The other alternative is to use threads. Threads are very, very similar to processes, at least from an OS perspective, but they share more things than processes do. They have the same globals, for example. So today I thought we'll take one of our simple servers, and then we'll try to not do it with not do this multiple clients with select, but we'll do it with fork first, and we'll see what happens if we try to serve multiple clients with different processes, and then how we can get these processes to interact again, because they're supposed to be independent. So my goal here is we'll have our simple client, our simple server, and it doesn't only like output what I type as a client. It also counts the number of lines it's received. That's it. So let's try to do that. With select, it's pretty obvious, right? To get all these reads coming in and use to increment some global variable. Let's try to do this with fork, and we'll see what happens. I think we had a pretty basic one. Okay, so this one looks pretty good. So let's see, what does this server do? It waits for a single client, and then it waits for a bunch of receives and just says welcome every time. and then writes out whatever you're saying. I think that's all it does. Let's get rid of this junk. So we'll save this as a fork server. Okay. So let's start out by just trying it out. Okay, maybe I should fix that so we don't keep having these errors. Where could write be? It's not in standard I/O. Is it control? Is that?
Yeah. It starts with ins.
Huh.
It says UIO.
Great, I don't have the developer man pages. We'll just get them from a Linux machine. Yeah, Googling it is fine too. Usually you get the man pages, but we're gonna be command line people here. And we gotta remember our passwords. Uni.std.h. Thank you. I'll just add it there. Okay. And we gotta get the right profile in here.
Seriously, checks for that.
Klein seems to be very anal about these sort of things, but I mean that's probably a good thing. And the error messages, I'm not used to Klein, but the error messages, they're very verbose, but they also seem to be quite helpful. So they have a little more information in them than what's possible with GCC. Well, this is not actually GCC anymore, just an alias for this new compiler called Klein. Anyway, so we're running it. Let's talk to it. Okay, so that's working. Close that. Let's see. There. That was not NC, it was telnet. Okay, so now the server stopped. Okay, so that's not what we want, right? We want to have now a while loop here, so we keep doing it. While true. Okay, so everyone can predict what's going to happen here, right? It'll work. We'll get one call, and then once it quits, we're going to get out of the receiver because then we get a 0. So now we get out of the while loop, and we go around, and we're going to wait for another client. That's all that's going to happen. Not too exciting. What we want to do is talk to 2 clients at the same time without using select now. So one solution there would be to fork. So I'll say if not forking like that. Okay, what did I just do? I start another process, a copy of the whole thing, and I say, here, if I'm the client, right? If fork returns 0, then I'm the child, and then I'll do this stuff. Now something weird is going to happen, because once that client quits, we're going to exit this, and now we're going to go around, and now we have suddenly 2 forks here, 2 processes trying to do this accept on the same server socket. It's going to get messy. Let's not go there, so we'll fix that part. We'll just, once we've handled one client, we'll just quit. Okay, so now what's going to happen to the server side? We're accepting something, we immediately fork, child goes off and handles that client, and our server comes back and now tries to accept again. Waits for the next one coming in. So that looks pretty good, let's try it out. This looks very simple compared to select, right? Just regular control flow, nothing fancy. Oh.
I was thinking if that's going to work.
Does it work with a different standard? No. Okay, fine. No, no booleans defined apparently. Okay, so let's just try it out. It's good to verify the steps along the way here. Some garbage there. Okay, I don't know. I must have hit a key by mistake somewhere. I can't see it, so I don't know what this garbage is. Anyway, so that seems to work. But now we wanted to count the number of lines that we received. Right? So how do we do that? Let's put in a global. Okay. Line count. And then for every line I get, I'm also going to write out what? Okay, so maybe the problem was here. I'm mem-setting this buffer here. It wasn't mem-set the first time. That was probably the problem. So that little garbage we got there. Yeah, here we are. This is a bad idea. I'm writing out the Stirlinen buff, not the number of characters I received. I'm not receiving a string terminator from the other end. So unless there was a string terminator just sitting there, this would not necessarily work right, and that's what happened. Okay. Maybe we'll just fix that too while we're at it. And good C style says you should write it like this. If you do an assignment within the loop, you want to put extra parentheses to make that clear that there's an assignment. This is not a comparison that we did by mistake. Okay. So where are we at? Yes, we're printing out the new lines. Okay. So let's run our. Oh, thank you. Let's run. Oh. Did I not put this? Yeah, I didn't put this reuse thing in it. Let's see where we have it. I don't have it there. Ah. That's probably a good idea. There. Beautiful, thank you. Okay, so one line count is 0. Oh, I'm not incrementing. Let's do that too. Okay, so it's off by 1, who cares? What's going on here? It doesn't look like it's incrementing. Exactly, we got 2 different programs running here. They don't care about each other at all. So, I mean, this is kind of silly. Most programs you implement are not going to be interested in doing a shared line count, but they will want to do something else that's shared. Right? So we'll use it as a proxy. So, how do we get them to have a shared line count? A shared library. How does that help? Doesn't actually help. So the library could have a global inside it. But it turns out that with this global offset table, they actually have different copies of the 2 global variables. A file? Yeah, we can stick it in a text file, and then we can read and write from it every... Right. So that actually is what we're going to do. But there's a better way. We don't have to open and read and write. There's another way to deal with text files, or deal with files in general, that we've talked about before. mmap. Alright, so I want to memory map the file into part of my memory. So now if I have 2 processes, and they both mmap the same file into some part of their memory. It doesn't have to be the same place. Now it's the same file. So now if I write to this part of memory, the other process will see the changes. All right, so let's try that out.
But they still have different page tables and stuff.
Oh yeah, everything's different for processes, but they so happen to tell the OS that I want this file, and they both get the same file. Then it's actually going to appear as a file on the disk as well. So now we could say these are actually, yeah, there's going to be for every fork here, there's going to be a new process, and then there's the server as well. What do we? I guess the server doesn't care. So we'll just say for every one of these, we open up this some shared file. So let's call it shared FD. It's not going to be a text file, so I'll just make it like that. What do we need? Read, write, create, and some nice read permissions. Well, you know, actually, that's a good question. So you can do it both places. And maybe I shouldn't do it after the fork. So here, now I'm opening it, and then I'm gonna mmap it and do all this work, right? But if I do it before the fork, they're all gonna get a copy of all that work anyway. Right? They're all going to have an open file descriptor to the same shared memory. So I might as well do it before the fork. It's not that it's going to make a big difference, but you know, it's actually not even there. I want to do it here. So before everything. So now they're actually going to have an open file for, they're all going to have an open file for this temp shared. And now we want to mmap it, so we go, call it shared like that. How's this? It's this size, I think. Oh, we have to tell it how big we want the file. So maybe it's like that. Yeah, file descriptor and then length. Okay, so I want a 100-byte file. Ftruncate actually goes both ways. So it just says, if you have a megabyte file, it's going to make it 100 bytes long. But if I have a 0-byte file, it'll also make it 100 bytes long. I wanted a 100 byte long file. So there you go. Okay, and then I say, okay, mmap 100 bytes of that file into memory. We want to be able to read and write. I better make sure I get this right here. Yeah, so we want to read and write. So there's some protection flags here. Read and write. The rest isn't important. Some other flags. Yeah, that flag is actually important. You can do map shared or map private, and it absolutely has to be map shared. I'll tell you why in a minute. And then finally, I think we have to tell it which file. Yeah, shared FD, and start at the 0th byte in that file. Okay, so we're telling the OS here, we want that file, whatever shared FD has open, in memory, wherever. The 0 here means I don't care where you put it, just put it somewhere and give me the pointer. You can also tell it I want it in this particular place, but then there are no guarantees that whatever used to be there is still going to be there, or that it's going to work out. And we don't care. Okay, we want to be able to read and write, and then there's this thing here. So there's two ways to open or to mmap a file. There's shared and there's private. With shared, if you write to it, whoever else has this file open, they also see those changes. If you make it private, then you're able to write to it, but no one can see your changes. Right? The way that works is you try to write to it, there's a page fault happens, and the OS sees, oh, that's mapped private, I'll just make a copy of this page. Right? This whole page that he's trying to write to, make a copy, change the page table, forget about it. So now the process is writing to their own copy of this part of the file. Okay, with map shared, that's for shared memory, so that makes sense in this case. Okay, so we have a pointer to this memory. Actually, let's make it maybe an int pointer instead, because then, okay, even call it counts. So this is an array of 100 bytes here, so that's a whole bunch of these ints. But we'll just use the first one. Okay, so then we'll say counts here. And I was incrementing in the wrong place, wasn't I? So I'll do it here. Counts 0 plus plus, right? So here I'm saying this is really an int array, right? So now I can dereference it as an array nicely and just increment the value. Yeah, good question. So I was provided memory by the OS here. Whenever the OS gives us memory, it has to be zeroed out for security reasons. So that's fine. But that's a very good question. Okay, and then we have to fix this. Counts. Okay, I think we're good. Yeah, so much for that. Prot read, prot write. Ah, okay, so this is, I didn't include mman, I think. Anything else? Oh, create. There's no E in there. Yeah. For some incomprehensible reason, there's no E in O create. There we go. There's that. And all the bytes.
Yeah.
Okay. 1. Doesn't look quite right. It's a little bigger than we expected. What's going on here? Ah, let's see here. I think I already had a file called shared. I was playing around with this a little bit before lecture to make sure I don't make a fool out of myself. And now I did. Okay. 1. Ah, there we go. Oh, that's on the wrong machine. Let's not use that one. 2. Ah. Okay, so that seems to work. So I've been saying this is also complicated. Doesn't seem so complicated, right? So let's see why this is complicated. For that, we can't rely on human input anymore. So we're going to have to make this kind of a different program. It's not going to be a fork server anymore. It'll just be a kind of a forker. Okay, so we'll drop some of the server stuff. In particular, I guess we don't want this. In fact, when we go like that, I don't want the loop either. I just want to fork a client off. Forget all this stuff. Just count this stuff. Count up a little bit. Oh, and then we'll have our line count at the end. Oh, but this is not enough counts. Let's make it a little more interesting. So we go that, do a few counts, and then of course we would expect this to print out 50,000, but let's just do it like this first. Okay, and then finally we will want to exit. Right, this is in the client, in the child again. We don't want the child to be sitting around, and we'll wait for the child to come back. So otherwise we're going to get a line count of 0 here probably. Right, child is going around this 50,000 times. We'll just drop straight through, print out the line count at 0, and or maybe like 15 or something. You know, a few lines into it. It's probably not going to be too interesting. Actually, why don't we try it out? See what we get. Alright, we dropped this crap too. Okay, so our forker. Okay, try it again. Oh. Oh, yeah, okay. That's maybe not so interesting. That's why. Let's go this way. So every time and then minus F so it doesn't complain. Okay. Okay, so it looks like it's 0 every time. That's probably it takes longer for the child to even get scheduled. So the parent is gonna just run on, and now the OS knows, yeah, oh yeah, I'm supposed to start a child here. So it starts working on that, but it doesn't quite get around to it before we go and print the line count. So let's just wait for the child to finish. See what happens then. What now? Oh, do I have to? No. What is it then? Here. I don't know. It's the this update that I need a status. Okay, fine. So what comes out in the status? Anyone? Or like the reason why it continued again. So it's waiting, and then sometimes it continues because it got a signal. Like someone hit Control-C or something. So it doesn't always stop waiting just because the client finished. Okay, but we don't care. In this case, we're just trying out a simple example. Okay, and then we had our clever one-liner here. Okay, that's nice. That's what we expect. Let's do another one. What do you think? Oh, I need another weight, don't I? What value are we going to get?
Oh, aren't like two processes trying to add stuff at the same time?
Yeah, they're just adding to the same int here. It is an int, basically. Yeah.
Can they do it at the same exact time simultaneously? Because we're not waiting in between for it, we're just waiting at the end. So for some period of time, both children will be editing the same file.
That's true. Close to 100,000, but missing some. Okay. So it's going to go over 50,000, is it?
I think it's 150,000, but also one child might report the wrong line counts because one is still counting up.
Yeah, the children don't actually print anything. It's only the parent at the end that prints. We're just counting, yeah. So we got 100,000 there. We got some crashing potential over here. 150,000. Wow. Where'd that come from?
That's one at fork again before process before.
Oh no, see it exits here.
Oh.
So that's fine. But we do end up with two children running probably concurrently. Let's just try it. There. Let's try it again. Look at that.
Oh, there was a locker.
Huh. You get a different result every time. So this is the general problem with concurrent programming. You don't know what the hell's going to happen. So there's some ways around it. If you, yes, of course. A nice safe way here would be to just have this guy increment count 0 and this guy increment count 1, let's say, and then just print out the sum of the two. Actually, is that safe? What do you think?
Yeah. Because of the same word, yes.
They're relating to the same file, right?
The same word, right?
Yeah. You type of
Oh. What about that? Okay. So,
It is the same word, right?
same word? No, there are two different ints. Certainly same mmap region, yeah. So this actually depends on the memory consistency model of the underlying machine, which is not part of C. Actually, now it is. With C11, C++ 2011, it is part of the memory consistency model, but it so happens that Intel machines do it this way. So it by word, even though they share a cache line, right? So now you have two CPUs with their own copies, with a different cache line copies of the same stuff, and they're writing to it, and they resolve that. They're both like sending signals to each other, saying, "Yeah, I'm also trying to write to the same thing here. Don't, take it easy." And they figure it out. It wouldn't have to be like that. It could be like anything within 64 bytes is all going to get obliterated. But this certainly makes things much easier, and any sane architecture would work this way. Okay, so we have a big problem. Let's back this up, because we want to know why is this? What happened? I'm guessing you haven't seen this phenomenon before, although there was a couple of hints here that maybe someone has, because the thoughts were a little too coherent. Whoa, look at that. Nice. We got a correct results. Yeah, unfortunately. Yeah. Yeah. Okay, so instructions in CPUs in general, they tend to be atomic. If you'd write to a word, you're not going to get like a half word written and then someone else comes in and get the other half of the word. That's just not how it is, at least not on Intel. I would hope not on any other modern CPU. Same with reads. You're not going to be reading like, you got half the word and then someone came in and wrote so you got the other half of the word after. That doesn't happen. Right? It's a 64-bit memory bus. You just say, get me that, and no one else can use the memory bus at that time. So it's atomic. So why does this happen?
It's maybe because one says, I'm going to read what's there. They read it, well, the other one is writing, but they still have the old information. So the moment they write an increased counter, the old information is back.
Yes. Right. So if I was to say over here, I just write count 0 equals some large number. And down here we say count 0 equals some small number. We're going to either get the large number or the small number. It's never going to be a mix of the two, but because those are atomic. But the plus here is not one instruction. It looks like one instruction. But if we compile it, where's main? Okay. Wow. This looks so different. Anyway, here's our plus plus. I think. So that, anyway, I don't know if that is the plus plus that we're talking about, but that is how a plus plus is implemented. How do we find? So there's a plus plus in the for loop as well. So that we might be confusing one for the other. There's a mmap. Let's see. There ought to be another plus plus. Oh, here. That's the one. No, this is on the stack.
No, below, there's a fork down there, so it's below the fork, right?
Well, there's a fork in other places. So we have two copies of it, right? First fork and the second fork. Let's see. Where's the first fork? There's the first fork.
Yeah, I think it's using different plus pluses depending on which iteration of loop you're using.
No. There's the I++ for the. Okay, let's
Oh,
go.
right, yeah.
Maybe 3 and maybe 9.
Forker. So there's that plus plus, and then there's this plus plus. So how can we tell the difference? This one here, the I is on the stack, and this is a global. Oh no, this is not a global. This is yeah. So that's in memory. So we're dereferencing some other array. Okay. So anyway, let's see what we can find out here. So here's one. It goes from RAX to E. So it's dereferencing. See, it's dereferencing a pointer here. This is a pointer posted on REX, dereferences it. And then here, we're just taking the value of something on the stack and incrementing it. So this is the one with the array, and this is just the I++. What's that? It's only? Yeah, so, but ints are 32 bits even on a 64-bit machine. So I guess the question is why, so here we have to get the full 64 bits because that's a pointer. But now we're just caring about the value. So that's it, 32 bits. I think that's true for both of them, yeah. Yeah, but this is just the value and there's the pointer. Yeah, okay, anyway, so this is the one. So our increment looks like that. So read the value from wherever, from somewhere. Here we're reading it from somewhere else. Increment it and then write it out. So now what could happen is I read the value, someone else writes to it, right, their value, and then I come back and write my incremented value, but that's based on the old value. So we're going to miss some other people's increments. It's a very simple example, but the same problem happens everywhere in concurrent programs. This is a sort of a classic, but there's a ton of this sort of thing. You can imagine a linked list. You want to remove an element from the linked list. Right? At the same time, someone else wants to insert an element right next to it. It's just a spaghetti of pointers all over the place, and it's not going to work out. All right, so that's what we need to deal with. There's a few different ways to do it, but I wanted to let's see. No, before we deal with it, let's switch abstractions here. So right now we're dealing with processes, with fork. But we don't have to do it with fork. So it got a little complicated here. There's all this mmap and all this other nonsense. The easier abstraction to use is threads. So why don't we try a thread version of the same. So for this we use a package called pthreads. pthread.h. Okay, so pthreads, or threads in general, they run in the same process. They share everything. They share all the globals, they share the file descriptors, they share everything except, any ideas? The stack, yeah. It'd be extremely difficult to know what's going on if you don't have your own stack. You can't even call a function because someone else might call a function and move the stack pointer on you. What's that? They share the same heap, yeah. That's fine as long as malloc is thread safe. You just ask for some memory and you get a pointer back. And it's not going to cause any confusion. Okay, so let's have a little function here. Call it a tfunc. And then we'll create a thread. Oh, actually, you need to go call it 1. Let's see, how does this go? Oh. Is it in 3? There it is. The stuff I don't get. Why do they have chapters for this stuff? Okay. So we got pointer. Then we need some attributes. We can probably ignore that. And we need a routine that we want to call, and then some argument to the routine. We'll ignore that too. So we'll go 0, and then we want to call tfunc, and then no arguments. Okay. So what's going to happen is a new thread, which is like a thread of execution, right? We're going to call tfunc, and we're running there, but at the same time we'll also be running down here. So we'll say and we don't know which one's going to run first and so on, but let's start by just getting this to run. Got an error. Second parameter of main must be of type what? Really? It is very picky. And oh, okay, that one I get. Okay. It doesn't care at all. Whatever, man. Okay, we're getting close. Let's include that too. Really? Huh. Okay. All right. There must be a way to tell it to be less picky, but I haven't learned that yet. Okay. Huh. So it works sometimes. So these are actually part of the same process, right? We have two threads that are part of the same process. What's happening is the parent keeps going, and then the parent is done. And then what happens when it leaves main? Well, then goes back to this start that we found early on in class, and in there somewhere is a system call to exit. And when exit is called, it'll kill the process. So sometimes the child doesn't have enough time, so it doesn't get around to running. But that's okay. All right, so now if we want to do the same thing here, let's do actually, can go like, oh, that was the wrong one. Anyway, okay, never mind. So now we can have a global. And we'll just say count plus plus. Forget that too, and that. Okay, and then we can print out the count. Huh. Okay, same problem, right? Because we don't, we're not waiting for our child to finish, so it doesn't seem fair to print this out before. So let's wait for him. Pthread, and it's called join here. Just pthread join 1, and then what is it? You need a return value. I think it goes like that. Oh, it's a void. Ah, yeah. So this is the return value from here. So it should really be a void star. Okay. Okay, cool. So that's working. So now we can run another one. In this case, I'll go like this. We'll wait for 1 and 2. Huh. Actually, we get a smaller value all the time. Huh. Was there a big one? 58. Yeah, but we got 100,000 once, remember? That was legendary. Anyway. So now these two threads, they seem to be kind of running more simultaneously. That's what's happening. It's pretty fast to create a thread compared to creating a process. So they're both running almost at the same time. So now for and all they do is go around here. So much of the time when they do an increment, they actually collide and get the same problem. So what we have to do is make sure that they don't read update, write this count at the same time. Right? So there's this whole part, this is whole little piece of the program that they can't run at the same time. It's not just one instruction, it's this whole thing. So that's called a critical section. So over here, is a critical section. Critical section means if you run two different threads at the same time, or in the case of processes and shared memory, same story. If you run two different threads inside of this critical section, you're going to get screwy results. We need to put a stop to that. So does anyone know? What do we do to avoid multiple processes, threads in the same critical section? Oh. What did you say? Tell them to stop and wait for the other one. Yeah, so what do we say? Oh, I see. So we can do a join. Yes. So there's an option. So we can actually do it this way. Here. All right. Oh, I just need to put this one up here. Look, it works every time. It's beautiful. What's the problem? This is not actually getting us very much, right? So now we're making a function call in a complicated way, and then we're waiting for the function call to finish. And then we make another complicated function call. So we might as well have just called pfunc here, without this whole pthread create stuff.
Even if we are doing it concurrently, it's still kind of pointless. It's just as fast with one function. Because you can't really parallelize that.
Yes. So in this case, we have a very dumb program. So in this case, it is pointless. It would be better to, well, I suppose what you'd want to do if you want to parallelize it is to have two different count variables and then add them at the end. Right? But let's say it was a more complicated critical section.
People think the function having call different functions that are exactly identical.
Calling different functions doesn't help. Because the problem is they're writing to the same variable.
I've heard the words lock and mutex before, but I don't know.
Yeah, those are the keywords you want. Lock and mutex, exactly. So okay, let's actually before we get into that, let's. I have to correct something. We don't need a more complicated critical section. Let's say we had a program that looks like this. Like work for 100 seconds. All right. And then down here is this little critical section. That is just a critical section. Right? So we do some work, we do some whatever, and then we enter this here. So we have a very small critical section. Now the problem is, almost all the time, this is just going to work. Right? So actually, can we? Yeah, we don't have enough time, so I'll just try something here. Let me do a little for loop here. J equals 0, j smaller than 10,000. J plus plus. Okay, we'll just go like that and hope it doesn't get optimized out.
This is the count plus inside of it?
This doesn't do anything.
Oh, okay.
Yeah. But it's working, not for 100 seconds, but for some time. Let's see. Oh, are we joining here? Yeah. That's. We could expect to get the same result anyway, maybe. I don't know. Let's see. Well, it's pretty close. Yeah. Man. So the solution, of course, would be to just increase this to 100,000. We're good. Right. Well, so if I did increase this to 100,000, it would happen almost never. And that's usually the case in concurrent programs. It almost never screws up. But then it does. And then you can't reproduce it. And that's why concurrent programming is so hard. You get these, they're called race conditions. You have these two threads, they're racing to get to the critical section. Usually they don't get there at the same time, but every now and then they get there at the same time, and then you don't know what's going to happen. You get a non-deterministic program. So next time we'll make the program deterministic. And actually, the rest of the semester, We'll be dealing with making programs, concurrent programs, deterministic and fast.
Stuff's important.
Yes, this stuff's important.